my name is Devin Johnson, and today I'll be discussing my research project on decoding fibroblast responses to tunable stiffness with tunable hydrogels. Now, looking at my research, I focus specifically on the human liver. Now, not only is the human liver one of the most largest organs in our body, it also has a lot of key functions that some of us may know. Some of the most commonly known functions are production of bile, blood sugar balance, and the detoxification of our system. However, throughout our lives, as the liver is in fact used more and more, there is the possibility of damage to the tissue within the liver. This damaged tissue can then create scar tissue, which will then increase the stiffness of the extracellular matrix of the liver itself. This progressional increase in stiffness of the liver itself is known as a liver disease, commonly called liver fibrosis. Liver fibrosis is the progressional increase of the liver itself. Now, this progressional increase in stiffness can inhibit the function of the liver itself, which can cause health complications for patients. Now, as you can see, from 1980 to 2024, there was a significant increase in cases around the world. So what that tells us is with such a significant health concern, we need to improve the way that we're researching this disease. Now, the two most commonly used modalities are tissue culture plates, which are far too stiff to give us honest results, and in vivo models, which have too many factors to trust that we could replicate the results to a human patient. So the goal of my project is to first develop a replicable 2D model that can replicate this liver disease. And then what we're hoping to do is replicate specific stages of this disease to study how cells respond at each stage. Once we have this platform, we then hope to study the mechanotransductive pathways involved with this specific activation of these cells. Through this understanding, we can look into future ways to treat or maybe slow down this disease. Now, in terms of materials and methods for this project, there was the polyacrylamide hydrogel fabrication. For this, we used simple polyacrylamide hydrogels. We then coated with collagen and seeded human dermal fibroblasts on them. We also used aminofluorescence staining and QRT-PCR for data analysis. Now, the first results from this project was definitively confirming the polyacrylamide hydrogels that we were using. For this, we wanted to optimize the ratios of acrylamide and bisacrylamide. We then used rheology to get the storage modulus, and then assuming incompressibility due to its elastic state, we can calculate the Young's modulus, which gave us about 1.5 and 4.5 kilopascals respectively. We were able to then define this as a significant enough difference in stiffness. With these gels, we then implemented them into our platform, and we first checked for aminofluorescence staining of the collagen 1A and alpha SMA protein. These are two proteins that are commonly linked to cellular fibroblast activation. We then quantified it, and as you can see on stiffer substrates, there's higher activation, but when TGF-beta or transforming growth factor beta is introduced to these cells, the activation is significantly upregulated, telling us that TGF-beta, when in these environments within the liver, does in fact play a role in the activation of fibroblasts. We then want to use QRT-PCR to check the gene expression of COL1A1 and ACTA2. These are the two genes related to the two proteins I had defined earlier. As you can see on varying stiffnesses, there is also in fact a difference in gene expression, with stiffer substrates having a significant gene upregulation compared to soft. Lastly, we want to see the specific mechanotransductive pathways involved with the activation of these cells. To test this, we use Y27632 or ROCK inhibitor, verteporfin and latrunculin A to see if the ROCK enzyme, YAPTAZ pathway, or actin polymerization do in fact play essential roles in the activation of these fibroblasts. When these three were separately inhibited, we noticed that with verteporfin and Y27632, activation is inhibited, as well as the mechanosensing of these cells is also removed. However, what's fascinating is that with latrunculin A, although activation is lowered, we do notice that the mechanosensing is not removed, telling us that actin polymerization may not play as an essential role in the activation of these cells as the YAPTAZ pathway or the ROCK enzyme. Lastly, in terms of future directions, we're hoping that this 2D model can serve as a baseline for future 3D models. Now that we understand the cell to matrix responses, we can look specifically into the cell to cell responses. And ultimately, the goal of these models is to be used for patient-specific care for things such as regenerative medicine and toxicity testing to specific treatments. Thank you.